Today, we tackle a problem that asks if we can transform one array into another by repeatedly reversing any subarray. It sounds complex, but the underlying principle is surprisingly simple. Can you figure out the core property that remains unchanged? Given two integer arrays, target and r, both of the same length, we need to determine if r can become target by performing any number of subarray reversals on r. The challenge is to efficiently check this equivalence, understanding that reversals can reorder elements but not create or destroy them. A straightforward approach is to sort both arrays. If r can be transformed into target by any number of subarray reversals, it implies they must contain the exact same elements with the exact same frequencies. Sorting both arrays puts elements in a canonical order, making direct comparison trivial. We sort target, sort r, then iterate and compare element by element. If any pair doesn't match, they can't be made equal. This approach has a time complexity of big O of n log n, linearithmic time due to sorting, and big O of 1, constant time space if an in-place sort is used. The key insight here is that reversing a subarray only changes the order of elements, not their count or value. This means if r can become target, then both arrays must be anagrams of each other. They must contain the exact same elements with the exact same frequencies. We can leverage this by using a frequency map. Since the problem constraints tell us element values are between 1 and 1000, we can optimize a traditional hash map to a simple integer array. We'll declare a frequency array of size 1001. First, we iterate through the target array, incrementing the count for each number in our frequency array. Then, we iterate through the r array, decrementing the count for each number. Finally, we check if all counts in our frequency array are 0. If any count is non-zero, it means there's a mismatch in element frequencies, and the arrays cannot be made equal. Let's trace this with target as 1, 2, 3, 4 and r as 2, 4, 1, 3. We initialize our frequency array all zeros. First, for target, we see 1 increment frequency at index 1, then 2 increment frequency at index 2, and so on until the frequency array reflects one count for 1, 2, 3, and 4. Now for r, we see 2 decrement frequency at index 2, then 4 decrement frequency at index 4, then 1 decrement frequency at index 1, finally 3 decrement frequency at index 3. After processing r, all counts in our frequency array are back to 0. We then iterate through the frequency array. Since all counts are 0, we conclude the arrays can be made equal. The algorithm correctly returns true for our example. This is because both arrays contain the exact same elements with the exact same frequencies, meaning r can indeed be reordered to match target through subarray reversals. You'll often spot this frequency counting pattern when a problem involves checking if two collections have the same elements or if operations only reorder but don't change the constituent parts. Look for problems where order doesn't ultimately matter, but content does, or where element values are within a constrained range allowing for array-based frequency maps. The time complexity is big O of n because we iterate through each array once. Space complexity is big O of 1, constant time as the frequency array size is constant, based on the problem's value constraints. This frequency map technique is powerful and applies to many problems. Try the next problem involving anagrams, same pattern. If you found this helpful, hit that like button and subscribe for more concise DSA explainers.